London, its people, the people who built it, in fact, all life on Earth are only here by chance. 99% of all the species that ever lived have been wiped out in a series of catastrophes, disasters that changed the course of evolution. 650 million years ago, the Earth froze. It pushed life to the verge of extinction. But if it hadn't, then life today would be little more than microscopic slime. This is the story of Snowball Earth. When we think about how we evolved from being single cells to what we are today, we tend to see it as a pretty calm process, don't we, with animals slowly transforming into other animals. But that's only part of the story. The reality is much more brutal and violent, with creatures hanging on for dear life while disaster after disaster threatens them with extinction. It's almost impossible to comprehend the immense time scale of our planet's lifetime. So imagine the whole of Earth's history compressed into a single day. Each minute represents around 3 million years. At midnight on our clock, 4.5 billion years ago, the planet was born. 2 minutes later, the first catastrophe struck. A protoplanet, Theia, smashed into the infant Earth. And in its wake, the first life appeared. By 8 a.m, there were shallow seas full of simple bacteria. Gradually, over the next 2 billion years, the planet stabilised, though life remained as single-celled organisms. Until 12.5 hours later, at 8:27 p.m, 650 million years ago, disaster struck again. The planet froze. Temperatures plummeted. Ice spread down from the poles. It encased the planet in a layer thousands of meters thick. A snowball Earth. Life had only just got started. Now, it seemed doomed. There are no traces of these ancient ice sheets left. They're long gone. But there are still clues that can tell us about this dramatic ancient ice age. The evidence is hidden away in some of the world's most remote places. These are the Flinders Ranges in the Australian outback. Today, it's one of the hottest and driest places on Earth. But geologist Jim Gayling knows that the rocks here provide direct evidence of our planet's frozen past. The area is so vast, the best way to investigate is from the air. There's a disaster story written in these layers of rock. You just have to know how to read it.
It's really like looking at a book made of rock. Every single layer has a secret on it. We look at these rocks as though they're a history book.
With the help of aerial photographer Tim Beyer, they spot an unusual rock formation in a dried-up creek. It's the evidence Gayling's been looking for. A 650 million year old rock called a dropstone.
A dropstone is an exotic piece of rock. They shouldn't be mixed in with mud and sand. They should be together in boulder beds or gravel beds. But there they sit.
The rock may look insignificant, but it's a major clue to the powerful forces that created the frozen world of Snowball Earth.
This rock shouldn't be here. It's sitting in a rock composed of mud, silt, sand and gravel. And normally that's impossible. The whole lot now is one big rock.
There's only one force that can carry rocks like this around the globe, and that is ice. There's not a lot of ice in Australia today. So, to investigate how ice could have moved rocks around the world in the ancient past, glaciologist Shad O'Neill scales the sheer walls of the Matanuska Glacier in Alaska. It's the closest we can get to our distant icy past.
We're taking a look at the rocks that are being transported down the valley by the glacier. And to do that, we need to go down there.
Glaciers are nature's bulldozers. They smash everything in their path. They gouge stones and rocks from high up in the mountains and carry them down the valley.
Rocks as big as buses can be transported for miles across the landscape by a glacier. I mean, the longest glaciers are hundreds, if not thousands of kilometers long, so you can move rocks over long distances.
When the ice melts, it deposits debris at the base of the glacier. This glacier is only a few hundred meters thick, but it can still carry thousands of tons of rock.
The glacier brought all this stuff down from the mountains, and when the glacier melts away, it ends up looking like a building site that's been bulldozed.
The Matanuska Glacier transports rocks for over 24 miles. It's the same process that carried the ancient drop stones in the Flinders Ranges. But the glaciers of 650 million years ago carried them for thousands of miles.
Here's a great example of a rock that was picked up by the glacier, carried down valley, and then deposited. Very similar to what you'd find in Australia, where glaciers used to be in the past.
So the Australian outback was once covered in ice. But that doesn't prove the whole world was frozen over. The problem is that the Earth's surface is in constant, very slow motion, pushing the continents to different places. So it's possible that 650 million years ago, when the drop stones were deposited, Australia could have been much closer to the cold South Pole. Meaning the drop stones were carried by normal polar glaciers. The solution to this conundrum can be found in another desert. Death Valley in the American Southwest. The term Snowball Earth was coined by geologist Joe Kirschvink, who's been gathering evidence on the theory for the past 2 decades.
Death Valley has a series of rocks that are extremely important for understanding Earth history. It's a treasure chest.
Like the Flinders Ranges, it's not the kind of place you'd expect to find evidence of ice. But geologists have found dozens of glacial drop stones here.
Every time I come here, I see new things. There are those big boulders, and I see one at the bottom, and they're all drop stones. You can see that they're coming in from the top. This is one of the best places in the world to see this type of geology.
The drop stones Kirschvink has discovered here date back to the same period as those found in the outback. So this desert too was covered in ice. But the big advantage is that we know where Death Valley was 650 million years ago. Every rock has a unique magnetic signature. This allows scientists to determine the point on the globe where the rock was formed. To study this signal, Kirschvink drills cores from the rocks containing the dropstones and measures their magnetic field.
The Earth's magnetic field is formed by electric currents flowing in the middle of the planet. The pattern of that field allows us to measure the latitude that a rock forms at.
When a glacier dumped these dropstones here, Death Valley was inside the tropics. The results at the Flinders Ranges were even more dramatic.
A group started studying the magnetism in the Flinders Ranges, and they thought they had a very stable magnetization. That they said, well, wait a minute, something might be relevant there.
The rock's magnetic signal revealed that 650 million years ago, Australia was in a completely different place than today. When the whole continent was in the grip of a big freeze, Australia was near the equator. Here was proof the scientists were looking for.
It was wonderful. It was the first time anywhere that we had proven that the glaciers were on the equator.
Ice sheets along the equator, the world's warmest climate zone, meant only one thing.
If you have ice at the equator, then the whole of the globe must have been covered by ice. And so you have to envisage a completely white planet.
Scientists believe it was the greatest ice age in the history of the Earth.
The entire Earth would have looked like Antarctica looks today. Even areas as desolate like this in Death Valley with nothing on it would be under several hundred meters of ice. The whole planet indeed would be a snowball.
Under a thick crust of snow and ice, the simple microbial life developing in the oceans faced an uncertain future.
This was the greatest ice age that this planet has ever known. You have to imagine a planet whose oceans were not only capped by ice near the poles, but that ice had grown across the entire planet and all but shut down its living systems.
650 million years ago, life on Earth seemed destined for total extinction. Somehow, something had plunged the whole planet into a catastrophic deep freeze. The question was, what? "8:27 p.m. on our clock of the Earth's history, 650 million years ago. The planet faced climate disaster, a global deep freeze. But what made it happen? Snowball Earth wasn't the first time the Earth had frozen, and it wouldn't be the last. Our planet goes through an ice age about once every 100,000 years. Most of them are caused by changes in our orbit. The further away from the sun we go, the colder it gets. At the height of the last ice age, ice sheets covered around a third of the planet, and all of this would have been buried under hundreds of feet of ice. But factors like orbit and rotation aren't enough to explain ice stretching right down to the equator. That must have taken something far more dramatic. The smoking gun turned out to be our atmosphere. Specifically, greenhouse gases like carbon dioxide.
A greenhouse gas is any kind of gas which has the capacity to convert the sun's rays into heat, making this planet the warm planet that it is today.
But it's a delicate balancing act. If CO2 levels grow too high or too low, the climate spirals into chaos. Too much carbon dioxide and the planet warms, too little and it cools.
Carbon dioxide is a very important gas. It's both our dilemma and our solution when it's there in too great a proportion that overheats the Earth, which of course we're worried about today. However, in the time leading up to Snowball Earth, we had the opposite problem. There wasn't enough carbon dioxide, and the Earth began to cool to a point where there was a runaway refrigeration that locked this Earth up in an icy crust.
Gehling believes that a drop in carbon dioxide levels caused the Snowball Earth disaster. Something was removing the CO2 from the atmosphere on a huge scale. And there's only one process capable of doing that: weathering. Carbon dioxide mixes with water vapour to form acid rain. The acid reacts with the rocks it falls on to form new carbon chemicals in the water. It then washes down to the sea, where it helps form solid limestone. Carbon dioxide that was once in the atmosphere is locked away on the ocean floor.
When weathering occurs at a great rate, you strip away rocks with acid rain, and that takes carbon dioxide out of the atmosphere and makes sure that it's locked away in the ocean.
Weathering happens more quickly when it's hot and humid. Normally, at least some of the Earth's land masses are too far north or south for weathering to be a major factor. But 650 million years ago, all the Earth's land masses, from Death Valley to Australia, were clumped together into one big supercontinent at the equator. The weathering process went into overdrive. CO2 levels crashed, and so did the Earth's temperature.
You have carbon dioxide being taken out and not replaced, and as a result, the Earth inevitably has to cool until you have a snowball.
Today, plants and animals help balance the levels of carbon dioxide in the atmosphere. Plants absorb it, animals breathe it out. But 650 million years ago, the only life forms on Earth were single-celled bacteria in the oceans. And they were actually making the situation worse.
650 million years ago, this is a world of cyanobacteria. Bacteria that formed a slime layer on the seafloor. Cyanobacteria are tiny organisms that have been around on this planet for 3 billion years before Snowball Earth. But at this time, they were particularly important.
These cyanobacteria sucked even more carbon dioxide from the oceans and locked it into limestone reefs called stromatolites. Some of this ancient carbon dioxide is still trapped in fossilised reefs, like these in Flinders Ranges in southern Australia. When Jim Gehling pours a weak acid onto them, the carbon dioxide they locked away hundreds of millions of years ago fizzes out.
What you'll see is an effervescence. Those white bubbles are carbon dioxide that have been locked up in these stromatolites, being released back into the atmosphere.
Rather than stabilising the carbon dioxide levels, the cyanobacteria were depleting them further. In combination with weathering, they sucked the carbon dioxide out of the atmosphere and temperatures plummeted. Even then, the planet might have avoided a total freeze, until a catastrophic chain reaction pushed it to the point of no return. Seconds past 8:27 p.m. on our clock of Earth's history. Snowball Earth, 650 million years ago, and counting. Ice was creeping down from the poles. In a normal ice age, at some point it would have stopped, but this wasn't normal. The ice just kept on coming until eventually it reached a point of no return. As it did, it triggered a phenomenon that would push life to the limit. The Earth's surface is made up of land, open ocean, and ice. These surfaces all reflect sunlight differently, and that's the key to what happened next. This is the Arctic Ocean, at the point where the ice meets open water. Scientists call it the lead edge. And geophysicist Don Perovich is here to study how the ancient Earth tipped over into a catastrophic deep freeze.
This is the place where the ice that's frozen to the shore meets the open Arctic Ocean. But it's more than that. The lead is where there's water, the lead's where there's light, and so the lead's where there's life. We see whales going by and seals and birds flying above. It's an incredibly productive area.
Here, Perovich can compare the reflectivity, or albedo, of two very different surfaces, the sea ice and open ocean. His sensor measures the amount of sunlight hitting the ice and the amount it reflects back. Sea ice is the most reflective surface on the planet. It reflects 85% of the sunlight that hits it.
If we were to just go out there, just 100 yards away to the lead, the albedo would be less than 10%. And what's interesting about this is this snow-covered ice has the largest albedo of any naturally occurring surface on Earth. And the open ocean has the smallest. So right here, we have a contrast between the best natural reflector and the worst natural reflector.
Open sea reflects very little light back into space. It absorbs the energy in the sunlight, keeping the planet warm. 650 million years ago, the opposite happened. Earth's best reflector, sea ice, was replacing its worst reflector, sea water. When enough ice had formed, the remaining ocean couldn't absorb enough heat. So more sea ice built up. That reflected more sunlight, the Earth got colder, and that made still more ice. It was the point of no return.
Let's say we grow a little bit more ice. So we're replacing the worst reflector with the best reflector. We'll cool things off, we'll get more ice, and we'll cool it off more, and it builds upon itself.
A runaway freezing effect capable of turning the whole planet into an ice ball. It's an idea no one even considered until a few decades ago. Scientists only discovered it was possible when they were studying another kind of disaster altogether. A nuclear war. During the Cold War, researchers predicted that a nuclear holocaust could push enough smoke and dust into the atmosphere to block out the sun and initiate a global freeze. Russian climate modeler Mikhail Budiko was investigating this scenario when he made a chilling discovery. He calculated that if the ice sheets spread beyond 30 degrees latitude, that's as far south as North Africa, they'd reflect so much of the sun's energy that the Earth would reach an irreversible tipping point.
So when we have a system like the Earth with these feedbacks, one of the things that's talked about a lot is tipping points. You can think of it as you're in a boat rocking back and forth, not much changes until you go too far, and then you're in a new state. And Budiko's work said that if we moved the ice down far enough, we'd reach a tipping point and cover the whole Earth with it.
Budiko calculated that if the ice ever reached this tipping point, the planet would no longer absorb enough heat to keep the ice in check. The planet would be entombed in ice from pole to pole. The theory is that 650 million years ago, this was exactly what happened.
Instead of the world we have today, we'd have something that looked like this. A vast expanse of white, of blocks of ice tilted every which way, covered by snow.
The planet descended into the most extreme and least hospitable climate it had ever experienced. Eventually, the ice sheets collided, clamping their icy jaws shut at the equator. It seemed that nothing could survive in this frozen wasteland. And yet, incredibly, it was this catastrophe that brought about life as we know it. And without it, none of this and none of the people around us would be here today. "647 million years ago, 8:28 p.m. on our clock representing the Earth's history. The planet was buried under ice thousands of meters thick. Deep beneath the ice sheets, single-celled organisms, the only life on the planet, faced a stark choice: adapt or die. Bacteria that had evolved over 2 billion years seemed destined for extinction. Imagine if Snowball Earth happened today. Could we survive? Temperatures would plummet way below zero. Ice caps would spread out from the poles and engulf whole continents. Violent snowstorms would paralyze entire populations.
You could not run a nuclear power plant long enough to get through the Snowball.
Many experts believe we could find ways to live through a short-term ice age, but the odds of surviving a Snowball Earth are next to nothing.
If humans ever experience a Snowball Earth, we will quite bluntly be out of control. There is no way we could stop it. It would be easier to live on the surface of Mars, probably, than on the surface of Earth during a snowball.
Without food to eat or fuel to keep us warm, the ice covering the planet would become our tombstone. During Snowball Earth, the only living things were single-cell bacteria. Even their survival seemed improbable. But here we are. Life clearly did survive. The question is, how? The quest to learn how ancient organisms kept evolution alive has brought this lone microbiologist to Whiteout Glacier in southern Alaska. Here, Hazel Barton studies how life could have survived a global deep freeze. Her mission is to find signs of life in some very dead-looking frozen caves.
People used to think that caves were devoid of life, that there was nothing in there. But it turns out they're actually teeming with microorganisms.
Barton's searching for modern-day microbes living in this ice cave to learn how their ancient ancestors endured the Ice Age 650 million years ago.
If you look on the edge of the cave, you can see all the particle dust that's got lodged in the ice. And it creates a surface that the microbes can actually live on.
The cave runs beneath the glacier. Inside, it's 4 degrees below zero. Creatures that live in such harsh conditions are known as extremophiles. Barton takes samples of the microbes buried in freezing rock sediments at the base of the glacier.
I'm looking for some sediments that might contain microbes that have never been exposed to the heat. So the thing we remember about these bugs is that they love the cold, and they've actually evolved to live in those cold conditions. And because of that, if I was to take them outside right now into the heat of the sunlight, they die. It would be like taking us into the middle of the desert and dropping us off there.
Barton believes this dark sub-zero cave can shed light on how microbes adapted to conditions during Snowball Earth.
The majority of surfaces exposed on Earth would probably have looked something like this. So we're looking at the kind of conditions that organisms that survived that period would have been living on.
They're not just living on the ice, they're living in it too. Sunlight penetrates a few meters into the ice wall, and that's enough for the microbes to flourish.
We're still pretty close to the entrance right here, so I think there's definitely a lot of sunlight energy and enough for cyanobacteria to grow on. And they're probably in the ice. They're living in the ice right now.
The deeper Barton goes into the cave, the darker and colder it gets. But even here, life hangs on.
This is a community that looks like cyanobacteria. They're incredibly resistant to all kinds of stress that you would put them under. They can survive it.
During Snowball Earth, the ice was thousands of meters thick. Enough to block out nearly all the sunlight microbes needed to stay alive. Barton finds similar conditions even deeper into the cave. Here, there's hardly any light at all. But even in this dim, icy world, she finds microbes thriving.
So what we're looking at are microorganisms that have to adapt and generate energy when there is no sunlight. So what they do is they pull energy from the rock itself. They actually chew into the rock to get that energy.
Outside, Barton examines her samples on a field microscope. She believes these modern cyanobacteria have a similar structure to the ancient microbes that survived the Snowball Earth.
We're seeing cyanobacteria. There's a whole community living in that ice. Cyanobacteria really are these amazing organisms. They're very, very adaptive. They're one of the most ancient forms of life on our planet. They can survive some really extreme conditions.
Cyanobacteria have evolved amazing survival mechanisms. If our cells freeze, they burst their walls. If they dry out, they die. But cyanobacteria have evolved a cell structure that prevents rupturing in some of the most extreme conditions on Earth.
They've changed the structure of their DNA so it doesn't get damaged. If you were to take us and dry us, then, our DNA would be irreparable. You do that to a cyanobacteria and you just have to add water 100 years later, and within a few hours, it's starting to carry out photosynthesis again.
Just as some could cope with dry conditions, others could cope with ice. As the ice rolled over them, most microbes died, but the hardiest survived. Over time, strains evolved that thrived in the cold and dark, to become the ancestors of every living thing on Earth today.
Everybody thinks about these global catastrophes like it's going to wipe out all life. And it's like, no, these microorganisms have been going through similar things for billions of years. And they're adaptive and they change. And then they fill the niche that's left behind.
Barton's research proves that even in the most extreme conditions, in the ice, in the dark, life finds a way.
Short of an object the size of Mars hitting the planet, life will go on Earth. And events that we may think are, catastrophic just simply turn over a new leaf and we start seeing a different form of life on Earth.
The only reason we're here today is because life adapted and survived. But there's another puzzle. We're here, but the ice isn't. All that ice should have kept the planet so cool that it could never thaw again. And for 25 million years it did. Then something extraordinary happened. 8:35 p.m. on our clock of Earth's history. The planet's surface had been locked in ice for almost 25 million years. But at 8:37, a remarkable thing happened. The ice sheets started to recede. Something was warming the Earth. But it wasn't the sun. Believe it or not, the thing that would save the planet was actually inside the Earth itself, buried deep below the ice. This is Mount Augustine in the Aleutian Islands, one of the most volcanic regions on the planet. Augustine has been active for over 40,000 years, and it's still erupting today. Volcanologist John Power is here to study what it tells us about the end of Snowball Earth. Because volcanoes are the only things on the planet hot enough and strong enough to thaw a frozen world.
We're on our way to Augustine Volcano. It's one of the most active volcanoes in the region. Last erupted in 2006. It all comes to play here at Augustine.
A fiery hell lies under Mount Augustine's frozen surface. During its last eruption, millions of tons of lava and ash exploded into the atmosphere. So much material spewed out, the volcano actually grew.
We're about 100 feet higher than the summit of the volcano was prior to the eruption. This is some of the newest land in North America.
Power uses a field thermometer to take a reading from just below the surface.
We've got a temperature of about 95, 96 degrees centigrade. So the summit of the volcano is still very hot. If you wanted to cook some potatoes, fry up some eggs, this would be exactly the spot to do it.
There's no doubt Mount Augustine is hot, but it's hard to believe a volcano, even one this powerful, could punch through an ice sheet several thousand meters thick.
Where we are now has been covered with glacial ice as recently probably as 10, 15, 20,000 years ago. This was all underneath a glacier at that point in time.
When Power examined volcanic rocks here, he found evidence that 24,000 years ago, an eruption smashed its way up through the ice.
There is absolutely no problem for a volcano like Augustine or its neighbors to erupt through an ice sheet that could be either several kilometers or several miles thick.
We know it's possible because we've seen it happen. In 1996, the Grímsvötn volcano in Iceland erupted right through a glacier. It punched its way up to the surface through a kilometre of ice. The torrents of hot gases and ash blew a giant hole in the glacier. It melted ice at a furious rate. Flash floods carrying 45,000 tons of water a second raged for hours. But on a global scale, that's nothing. When the whole world was frozen, a few little holes wouldn't have made much difference. Luckily, volcanoes have another formidable weapon in their arsenal. They spew out more than just lava and rocks. They also produce huge amounts of greenhouse gases.
Carbon dioxide is one of the very dominant species of gas that is coming out of volcanoes. There have been times when we've had certainly, thousands of tons per day coming out of this volcano.
Mount Augustine is dwarfed by the volcanoes that broke through the ice of Snowball Earth. Scientists believe that thousands of them ejected billions of tons of carbon dioxide into the atmosphere. Over a period of around 1 million years, this caused carbon dioxide levels to rise, reversing the depletion that created Snowball Earth and tipping the balance in the opposite direction.
Carbon dioxide rapidly built up in the atmosphere until it got to a critical point where we had a super meltdown of the ice, and that was the death knell of Snowball Earth.
The carbon dioxide-rich atmosphere trapped the sunlight, increased temperatures, and finally melted the ice. After a 25 million year freeze, Snowball Earth was over. As the ice sheets retreated, something remarkable happened. The greatest leap in the evolution of life the world has ever seen. A leap that would lead directly to us. In the oceans, a few single-celled organisms had survived. After the ice melted away, they began to change dramatically. Roughly 3 million years after Snowball Earth ended, the new warm climate triggered an evolutionary explosion unlike any other. Single-celled bacteria evolved into multi-celled creatures. The first ever complex organisms and the ancestors of all animals, including us. It was the dawn of a new era for life on Earth.
Snowball Earth must have been the closest thing to extinction of early life on Earth that we had. And yet we know creatures survived. And it can't be a coincidence that very soon after the waning stages of this Earth-wide ice age, we get the first large creatures. It really seems as though that series of environmental catastrophes spawned the kind of biology that could give rise to multicellularity.
The key to this evolutionary revolution was oxygen. Before the deep freeze, oxygen levels were only 1%, too low to support more complex organisms. After the freeze, levels rocketed to 21%. Scientists suggest the boost in oxygen levels was the result of Ice Age chemistry. During Snowball Earth, the sun's ultraviolet rays reacted with water molecules in the ice to produce a chemical called hydrogen peroxide. When the ice eventually melted, the hydrogen peroxide broke down again, releasing huge quantities of oxygen into the air and oceans. The surge in oxygen levels provided the fuel for life to evolve from single to multi-celled organisms. They don't look like much, they're only the size of pinheads. But these tiny creatures are the oldest multicellular fossils on the planet. The first links in the evolutionary chain that eventually led to advanced animals and humans. In the new oxygen-rich atmosphere, these creatures became more and more complex, from just a few cells bound together to creatures large enough for separate groups of cells to assume different body functions. Over millions of years, these specialized groups of cells evolved into the first organs, and that paved the way for ever larger and more complex anatomies. In Australia, Jim Gayling studies the fossil remains of the creatures that inherited the planet after Snowball Earth.
After Snowball Earth, we see a revolution in the history of life from the fossil record, because for the first time, we see large creatures, creatures that anyone can see with the naked eye. They are the first animals on Earth.
This primitive sea creature is one of the first complex multicellular organisms. It lived and died around 50 million years after the end of Snowball Earth.
It's absolutely complete. You can see the gut, you can see the head end where the segments are wrapped around it, and these incredibly fine segments just wrapped over the sea floor.
All the animals on the planet, including us, are descended from creatures like this.
You're looking at the first life forms which had patterns of cells and body plans that were the same as ours. Head, a tail, a belly, a back. Even though they're not necessarily our direct ancestors, these are the first creatures that represent the line of biology that gave rise to us.
All over the planet, similar organisms were evolving, making the leap from primitive to complex life.
There'd been life on this planet for more than 3 billion years. And it was really only the Snowball event that kick-started complex life. If it hadn't been for this ice age, this would have been slime world forever, and we wouldn't be sitting here talking about it. So if you want to put your finger on one point in the history of life that made a big difference, that was Snowball Earth.
From slime to this, complex life in all its vivid, colourful, infinite glory. All of this, you, me, every living thing on the planet, is here because of an evolutionary explosion 650 million years ago, of a catastrophic deep freeze that threatened to wipe all life off the Earth, but ended up creating life as we know it. If it wasn't for Snowball Earth, we probably wouldn't be here. In the next episode of Catastrophe, massive volcanic eruptions kill off 95% of all life on Earth in the biggest wipeout of all time. But remarkably, this new catastrophe triggers the evolution of the most successful creatures ever to walk the planet, the dinosaurs.
You can discover more about the amazing natural events that shaped our planet at channel4.com/science. So, we have Steph, Mercedes, Nancy, Sarah, Zoe, Michaela, Amy, Sasha, Maliki and many more, all going later with Hollyoaks. Next.